Okay, great. Okay, let me share my screen one more time. All right. Welcome everybody to the atomic cross-ledger transactions between Besu and Corda ledgers using Hyperledger Cacti version 2. We would love to thank our presenters today, Dominic, Marilees, Peter, and Peter, who are going to take us through this fantastic program. Just a little bit of housekeeping up front. This is a Linux Foundation and Hyperledger Foundation event. It is held under the Linux Foundation antitrust policy. If you have any questions about these matters, please contact your company counsel, or if you're a member of the Linux Foundation, feel free to contact Andrew Updegrove of the firm Gesmer Updegrove LLP, which provides legal counsel to the Linux Foundation. This is also held in the Linux Foundation community guidelines, which can be summed up really simply: be excellent to each other. Bad behavior will result in you being kicked out, but we want everybody to feel welcome here, and that's our goal. Thank you for joining us. So the Hyperledger Foundation, we host the open source enterprise distributed ledger projects, tool sets, frameworks, and their communities. There are numerous projects within Hyperledger. We're going to just really quickly go over, but this ecosystem is why we exist. We are part of the Linux Foundation, and we use transparent open governance as just part of our DNA. We have a diverse ecosystem of enterprise-grade technologies and use cases. So we both have distributed ledger projects that are, in one case, like Indy and Aries and Anoncred, specific to the identity use case. In other cases, things like Cacti, which are meant to be interoperable across different projects and chains, not just Hyperledger projects, but projects outside of Hyperledger. But they also fit within multiple use cases and industries. We have finance, CBDCs, healthcare, telecom, supply chain, climate action, education, and a lot of these are represented in our special interest groups within the Hyperledger community. When we talk about the projects that we have graduated, incubating, and Hyperledger labs. Generally, new project ideas start in labs. Let's see if we can build a community around this project and this code. Lab projects can graduate to incubating status. And I think a wonderful example of that is one of the projects we're going to talk about today, Hyperledger Cacti. Another project we're going to talk about today is the Harmonia lab. And so you'll see there's, Hyperledger Cacti started out, we went from a lab to incubating to graduated status. That's an example of how these projects grow and evolve. As you see here, we have both full DLTs like Fabric and Sawtooth and Aroha, and Indy. We have tool sets like Cacti and Firefly, frameworks like Aries, and then we have even an Ethereum client, enterprise Ethereum client in Besu. So that gives you a sense of the spread and the types of projects that we've got. But this is open source. This is not, we need you. We need contributors. We need maintainers. We need folks who believe in these projects, believe in these use cases, and want to see change. And we're powered by the community. We are focused on the community. We do not exist without the community and the contributors and the maintainers who make up these Hyperledger projects. And we both sincerely thank them, but also we would encourage you, the attendees of this workshop, if there are things here that you're interested in, if there are things here that you want to influence, if this is work that you want to do either for your company or for yourself, please, by all means, we are an open community. Everybody is welcome here. We communicate via mailing lists. We communicate via Discord. We communicate via working group meetings. And so there are a couple ways to get involved. You can sign up for a Linux Foundation account. You don't need to have a Linux Foundation account if you want to join a call. You can look at the GitHub. Our GitHub repos are all open. You are more than welcome to come in there, get involved, play with the code. In a lot of our projects, we have a good first ticket tag. So if this is something like you've got experience in Solidity and you want to check out Besu, there's probably a good first ticket you could check out there. And the maintainers and the contributors work really hard to make sure that we've got on-ramps for folks who are new. That's the only way these projects can grow and be healthy and viable. We have contribution guidelines for most projects. We have working docs and the wiki, and we have communication channels that I just mentioned: email, Discord, and live meetings and events. That is it. For my part of the presentation, I'm going to stop sharing and turn it over to our fantastic presenters and let them introduce themselves. I will be posting links in chat. If you have a question, please post it in chat. I'm going to be capturing the questions, and we're going to, at different intervals throughout the workshop, we'll be going through the questions. In some cases, when someone is presenting, one of the presenters might answer a question in chat. That's completely encouraged, and we love to see it. So Dominic, Marlies, Peter, and Peter, it's your show.
Thank you, Sean. Give me 1 second. Okay. I'm going to share my screen real quick, say a few words, and then we can carry on to the rest of it. Can you see the slides?
Looking good, Peter.
Okay. Welcome, everyone. I'm Peter Shumajvari. I work as a technology architect, and I'm one of the maintainers of Hyperledger Cacti. So we've brought everyone here today to show off the progress, what we have, both in Cacti and in the Harmonia labs. And we're hoping that in the future there will be more collaboration between the two projects. And so what you will see is first kind of laying the groundwork about what the Harmonia lab is, what does it do. And then I will give a very brief introduction onto the concepts of how can this be made work together with the Cacti framework components. The interesting bits there will be about how you can use the API server and the connector plugins of the framework to actually connect to the ledgers and perform the operations that you will have seen before in the previous talks of the workshop as well. And so, apologies. Yes, so Cacti, really quickly, is a pluggable framework that's meant to be enterprise grade. It's sort of an SDK of SDKs. So that's why you will see that first we build up from the content in the lab, and then we move on to the framework as well. And then the reason we created the framework originally is to address fragmentation. So if you have multiple different ledgers, then the complexity just shoots up for your software project, especially if you have to use different languages to develop for those different ledgers. It can get very complicated. So what we're aiming to do with the framework is to make the development simpler. And I'm always very open to feedback about what we could do better. Another thing that we try to lower is the risk of adoption, meaning that if you bet everything, not everything, but your project on a certain ledger, and then that ledger doesn't turn out the way you wanted it to, then you should be able to migrate away, and the framework should help you with that as well. So we are in the Hyperledger greenhouse. This is a slightly outdated slide because it still says Cactus, but the project has been renamed to Cacti. And this slide is a good reminder for me that I have to say that as well, just to make sure people know. Then we have design principles. The big one, for me at least personally, is the plugin architecture. It means that the GitHub repository that we have is actually consisting of, at this point, more than 60 different packages, which are all their own entities or components, in the sense that they all have their public API surfaces that we publish individually. and they all have their own release versions that we do keep in lockstep. But nevertheless, if we need to, we can issue separate releases on a per package basis as well. And then we want it to be secure by default, which means that we don't want to be the source of some data breach or security breach where it was very simple to break into a system just because the software used was insecure by default, which is usually a trade-off that people make with their software just in order to keep it convenient. And then the other big thing is that it's toll-free, which means that it's an open source framework, so you get the source code, but also there's no mechanism built into it that would charge you in any way. What costs the ledgers accrue is a different thing, but that's between you and the ledger. The framework itself does not have any sort of mechanism. And then low impact deployment, which means that we're trying to make it as convenient as possible to work with the framework and not have to re-architect your existing ledger deployments, for example. And I'll skip over a lot of the additional stuff because I don't want to be talking for too long. Yes. I talked about, yes, so the code is mostly written in TypeScript and Rust. And we have a big focus on test automation. We have a huge CI pipeline to verify all the 60 packages that I was talking about. And the mono repo itself, we use a tool called Learner to manage that, which means that the 60 packages, for example, if you want to build all of them, we can do that with a single command. Or if we want to issue a release, that's also just a single command to publish them. I will skip over the plugin architecture. Yeah, actually, I'll just skip over to the end, which is the interesting bit, that we have a community. We have a Discord channel, like Sean mentioned, and we have daily pair programming calls. So if you find yourself with questions after this workshop, then there's pretty much every day of the week, well, weekdays, at 10 a.m. Pacific time, a pair programming call that you can join to. And the link for that pair programming call is also on the wiki page on this link that I'm showing right now. And later on, I will post these links on the chat as well. Okay, so this is just to kick us off and talk a little bit about Cacti. And now I will hand it over to Peter and Dominic. They will also showcase what's in Harmonia Lab, and they will talk about the theories behind that a little bit as well. And then we'll come back to, at the very end, we'll come back to a little bit of a demo about how you can use Cacti to work with those as well. So that's it from me for now. Thank you.
All right, thanks, Peter. So what we're going to do now is talk a little bit about, as Peter said, about Harmonia. And before we do that, I just want to do some introductions. So Peter Munnings, I'm with a company called Adara, and we provide product solutions for banks and for FMIs in this distributed ledger space. Primarily, the one that's probably getting the most press at the moment is Finality. We're the blockchain partners to Finality, which is a central bank-backed cash settlement layer based on Ethereum, but connecting to multiple different other platforms for DVP or PVP, so cross-chain, cross-blockchain settlement. I'll talk a little bit more about that. But just to say that Harmonia really has come from a very tightly scoped set of problems that financial institutions and financial market infrastructures are trying to solve, and we've got to this place. So that's my background. That's where we're coming from. I'm going to do an introduction to Harmonia. I'm going to then hand over to Marlies, who's going to be showing some of the direct contributions that have come into Harmonia, which are largely based on the Enterprise Ethereum Alliance spec. And then we're going to hand over to Dominic Fox, who is going to talk through some of the differences and I suppose some of the discussions we've had over the years now as to how do we see interop happening between something like Ethereum, which is a pretty different construct to Corda. So he'll do a deep dive into that, and then he's going to show one of the other implementations that's in Harmonia, and then we will hand back to Peter. So before we jump into all of that, Dominic, do you want to do a quick intro? And then I will I'll slides up while you're doing that.
Yeah, so I'm Dominic Fox. I'm a principal software engineer at R3. R3 sort of chiefly the architects of the Corda distributed ledger platform. So we used to call it a blockchain, but it has some blockchain flavors to it, but it's also notable by being a private and permissioned network, which works in some quite different ways and does some quite different things to a lot of the public blockchains. And with a few colleagues, notably Eduardo Irina, who's not able to be here today, I think he's unwell, and Richard Brown, who's the CTO at R3. We've been working on Harmonia in partnership with Adara for a few months now. So yeah, I'm kind of excited to show our work from the R3 side, because we've both been contributing code into the repository.
Great. All right. So Project Harmonia, let's dive into it. So Harmonia is not one of these, which is a harmonium. Thanks to Dominic for introducing us to a harmonium. It's not a harmonica. It is an initiative driven by a group of banks initially, to help create common patterns and standards for interoperability between digital asset platforms in order to simplify the atomic settlement of delivery versus payment transactions. So there's a lot in there, but that's where it came from. Peter mentioned the problem that banks specifically are facing, in that they, as these distributed platforms grow and as they're needing to do more and more settlement across different platforms, what they don't want to end up with is a plethora of different gateways, interfaces, data formats, interop mechanisms, etc. So Harmonia really is a place where banks can kind of easily start to put in their requirements, so principles that they've defined. And let me just say up front, it's been a real pleasure working with Hyperledger, the Hyperledger Foundation, and they've made this process really, really easy. And it's a great, very well understood platform that banks understand how they can contribute into. So one of the problems we were having when working with different banks is that they all had various parts of their system that were proprietary, but they did want to somehow create these standard patterns. They all had some principles that they wanted to implement. They all had specific requirements, and as we looked at them, there were quite a lot of common requirements across the board. And so we decided to form a lab within Hyperledger, mainly to really be a dump initially for all of these principles, requirements, and reference implementations. But as we started working with Hyperledger, we were quickly introduced to different projects in here, and most notably the Cacti project. And because the aims of Cacti are quite similar, and because there's there's a reasonably mature interop product that's in there, one of the things that we are looking at doing is taking all of the requirements and the principles that the banks have started to put together, and then look at some reference implementation. So we started off with some basic reference implementations, which we're going to show you. And then, as Peter said, he will show you how you could do this using Cacti. So Harmonia is never intended to become a de facto product or a reference implementation by itself. It's meant to be a place where different products can say, this is how we would expect to implement what the banks require based on our product. So we expect a number of different reference implementations to be in there, and each will have different pros and cons. Just a little bit of our journey to get here, just to give you an idea of where we've come from. So much of the team at Adara that have been working on this were, well, some of the team, should I say, not much of the team, some of the team. We got together in 2017 on Project Ubin with the Monetary Authority of Singapore. And even back then, that was a project where they gave us a task to implement interbank settlement with netting across distributed ledgers. And there were three teams. There was an R3 team who built a solution on Corda. There was a team based out of Consensus and JP Morgan who built a solution on Quorum, which is an enterprise Ethereum client. And there was a Hyperledger Fabric team. Each of the teams were paired with different banks. So we had real world bankers who were giving inputs into exactly how this worked. And the Monetary Authority of Singapore, the central bank in Singapore, hosted and gave us a huge amount of input. It was very intense couple of months in Singapore building this all out, and you can go and have a look at the Ubuntu report, which was an interesting experiment, I suppose, back in those days. But we managed to get quite far in terms of the work that we did. 2018 in Canada, Project Jasper was kicked off. We weren't directly involved in that, but some of the R3 people were. And then 2018, I led, along with Kuni Besu, who's also on the call, a project called Project Corda. Corda is a Nguni word which means to pay. So it's a payments project, obviously, with the South African Reserve Bank. So back in 2018, we ran a network, blockchain network with 7 commercial banks connected to it, as well as the central bank. And it was the first real, I suppose, test net, if you like, of a central bank digital currency for wholesale settlement. And we did a number of actually fairly decent performance testing with the central bank to check to see that this technology was viable. And once again, you can go and read the Project Corda 1 report from 2018. 2019, Finality International was founded. So Finality International, as I said, has been in the news a lot in the last couple of days. They've just done a second or Series B funding round. They've just raised $95 million for their next currencies. They plan to go live with a production version of distributed ledger-based sterling, British pounds for interbank settlement. And they're looking to do dollars and euros next year. So they are a company that is very well embedded into the process. They've gone through all the regulatory process, and they're about to go live with some of the initial currencies. Adara has been the blockchain partner to Finality for the last 4.5 years or so. So we've helped establish and build out the blockchain foundation. 2020, we started the interop work with Finality, initially with a payment versus payment, so an FX type transaction, settlement across 2 different Finality currencies. Obviously, in those days, it was reasonably theoretical, although much of the production grade contracts were already in place at that point. In 2022, we did a collaboration with Finality, Novora, and ourselves, along with NatWest and Santander, to do a cross-chain debt issuance. We actually used public Ethereum for the debt instrument that Novora issued, and then permissioned Ethereum for the cash layer, which Finality were hosting. Also in 2022, we did, actually, sorry, I think that was 2021, might have been the beginning of 2022. Towards the end of 2022, we did a pilot PvP with Fintium. Fintium is owned by a couple of banks, and they have a intraday FX swap product that can settle on Finality. And so we had also 2 Finality currencies running at that stage in a pilot mode with Fintium. So probably POC is a better word, not real money at that stage, but using their production grade software, both Fintium and Finality. And then also towards the end of last year, we did with HKLX. HKLX is high quality liquid asset exchange owned by the Deutsche Börse, or partially owned by the Deutsche Börse in Germany, and backed by securities sitting on now a number of different tri-party platforms, but Euroclear and Clearstream are the primary ones. So it was a pilot DVP settlement. Is actually part of a repo trade, so a repo with cash for securities, and that was completed. And that was probably the one that we spent the most time looking at. How do we do this atomic swap between two different chains? HKLX is running on Corda, and Finality obviously running on Ethereum. So that's a little bit of history. As you can see, we've been doing this for many years, and working primarily with central banks and commercial banks and consortiums of banks, as well as securities platforms, as you know, and obviously as well as FX trading venues. So we've had a really good insight into how the regulated world sees all of this, and how some of the issues that they are facing. So some of the principles that have come out of the banks and the FMIs. So what this group of banks got together and said, you know, there's a couple of things that we want to see. So firstly, we would like to make sure that whatever principles or patterns or standards come out, they must be anchored in production implementations. So they're not interested in theoretical exercises. They want to know that there are platforms that are using these patterns, these interop patterns, and that was the number one principle. They said, we've got to start somewhere. So they wanted to start with a minimum set of wholesale business flows, including repos, so obviously the HKLX influence, FX swaps, Fintium, and then equity or bond settlements. So those were the three areas that they wanted to start with. There are a number of platforms, both cash and securities, that cover those, and so it meant that we could find a number of different real-world implementations to start looking at how we would do this. Initially, the minimum protocol scope, so they said we want to start also somewhere, Corda and Enterprise Ethereum, but obviously the idea is to extend that as and when makes sense. Also, one of the core principles was that we needed to be aligned to relevant standards bodies. So some of our team, and we've had some input from R3 as well, working on the Enterprise Ethereum Alliance Interop Working Group. So it's a working group that's specifically looking at interop between different blockchain ledgers, primarily focused on Ethereum, but Ethereum to anything else as well. So very interested. In fact, next week, Kunima or Marilis, I think you can talk about. I think next week we're doing a presentation with the EEA on a similar topic to this. Wanted to maintain community incentive alignment. So really what that means is that the banks want to make sure that whatever we propose that is implementable by the banks, and there is the banks as the kind of sponsors of this their incentives are aligned. So basically what that means, and I think Peter covered it quite nicely, they for example don't want to see any third-party tokens introduced in the process. They want to make sure that there's nothing that blocks any kind of innovation or blocks any implementation of standards. So very, very keen on making sure that as banks they could, anyone would be able to implement a solution based on the principles and the standards that get implemented. And then obviously want to see a number of different reference implementations in Harmonia, so that it'll help. We just find it's much easier when you can show people how it works rather than theorizing about how it works. And then one of the things that the banks also wanted to say is that they wanted the patterns to be anchored around the wallet or the asset holders, and not around bridges in the first instance. They're not opposed to bridges, relayers, companies that specialize in transferring data between different chains, but they wanted the focus to be around the asset holders. So just wanted to paint a picture of this is where Harmonia is coming from. It is very much from the regulated world that is now wrestling or grappling with how do they do what they used to do in the traditional centralized world in a decentralized manner. And so a lot of thinking, a lot of thought gone into how do we launch and get Harmonia going. Some of the requirements that have come out of some of the initial real world use cases is, and you'll see many of them are not technical at all, although there are some technical trade-offs that need to be made based on them. So firstly, any two platforms that are going to interop together need to have a very clear and a very well-defined rule book. So both platforms need a rule book as to how they are going to be doing their settlement, and they need a common rule book in terms of how they're going to do settlement between themselves. So Peter mentioned at the beginning how exponentially this gets more and more complicated. Technically, it also gets more and more complicated from a legal and a rulebook perspective. And so some of the work, which we don't really touch on in Harmonia, but some of the work that's going on at the moment is around how to align those rulebooks and try and simplify the patterns around interoperability. There has to be a legal basis, so there has to be law around that. So, for example, Finality have had to have a policy change from the Bank of England. Last year, beginning of last year, the Bank of England updated their policy on distributed ledgers and said that if a financial market infrastructure wants to run a distributed ledger using sterling, UK pounds as the settlement asset, they put together a policy as to exactly how that would happen. So it's called the omnibus policy. But whether it's commercial bank money, central bank money, securities, whatever they are, there needs to be a legal basis for being able to run the operation and law around what happens if something goes wrong. That has some implications because there is a legal fallback in pretty much all the systems that we've been working on. So if something does go wrong, there is legal recourse in terms of getting that resolved. So that the technology kind of supports that. Participation, it's clear that participants need wallets on both systems, or at least access through an agency bank to wallets on both systems. So all participants need to be able to legally own the cash and the securities on both platforms. There needs to be a unique trade ID. So this is quite an interesting one, is that for a number of reasons, legally, any settlement across multiple platforms has to be based on an agreed trade. So banks have to agree on a trade. Part of that trade is a unique trade ID, and then based on that trade ID, the settlement then happens on both chains. And that's something that we've had to bake into the process. It's one of the obvious kind of legal results of the work that was being done. The process is a two-phase commit. So at the moment, so there's a concept of earmarking the securities, earmarking the funds, checking the earmarks are in place, and then going on to the commit phase, which is the settlement. We'll talk quite a lot about that in the demo, so I'm not going to spend too much time on that. And then there has to be settlement finality. That's a key element of regulated market infrastructures. It's one of the principles for financial market infrastructures is that there needs to be settlement finality. It has to be deterministic, cannot be probabilistic. So, for example, timeouts are a no-no. There needs to be a deterministic settlement process and a deterministic cancellation process. So we explored at length, looking in the early days at things like hash time lock contracts, but we just couldn't get them through the legal and the regulatory frameworks. And then huge amount of work has been done on liability, and for the purposes of this conversation, it's important to understand the financial market infrastructures and the banks have determined that each platform is responsible for providing a cryptographic proof that either earmark has been placed or that settlement has occurred, and that cannot be outsourced. So there's no ability in law at the moment for a bank or for a platform to be able to outsource the checking or the validating of that because the platforms at the moment are responsible for providing the cryptographic proof. So that's quite important. And Dominic's going to spend a bit of time exploring what that really means, both from a Corda and an Ethereum perspective. He's done a huge amount of work digging into that. Who's contributed to Harmonia so far? So currently it's R3, Adara, and Finality. We'd be very keen and very open to having others to contribute. We've had others who have contributed through us in some manners, not prepared to contribute themselves, but certainly they've given us material that we can put in there. But at this stage, we'd like to expand it. So Harmonia is a couple of months old now, and I think we're at the point where looking to expand the pool of contributors. We're going to jump into some demos now, but I'm going to pause there, and I see there's some questions coming in. So let me stop sharing. How do I do that? Can't seem to stop sharing. Oh, there we go. Stop sharing. All right. So let me maybe answer some of these questions quickly. Jim Mason, is earmark a hard or soft allocation of assets? It's a hard allocation of assets. So in the traditional world, if you think of clearing and settlement, it's the clearing process. So I see Kuni's answered that already. Great. Thank you, Kuni. Yeah, so you can only free up those assets for use somewhere else. So there's no rehypothecation or anything else. It's a hard allocation. Any other questions? All right. Marlies, I'm going to hand over to you then to go through the demos.
Hello, my name is Marlies. I'm an engineer for Adara. I'm going to run you through a demo that we have, or the code that we've contributed to Harmonia. Can everyone see my screen okay, or is it a little bit small?
I felt the font size.
Can you see the console? Okay, I'll zoom in.
Yeah.
So I'm going to show two flows, a PvP flow and a DVP flow. The PvP one will be between two Ethereum ledgers. So we're going to do a FX swap. We're going to swap some dollars for some pounds, both being Ethereum chains. And then we're going to go over to the DVP, where there are securities residing on a Corda ledger, and we're going to swap them for some cash on the Ethereum ledger.
Just a quick comment before Marlies carries on. Just I know we use these terms in our world a lot, but PvP is payment versus payment. So it's payment of one currency for payment to another. So typical FX settlement. DVP is delivery versus payment. It's actually delivery of securities versus payment of cash. So that's where the PvP and DVP come from. So when you hear PvP, it's effectively two currencies, an FX type deal. DVP is typically a security for cash. So just in case you were wondering.
First, I'm going to show you quickly before I run the demo on the right-hand side, just setting up the infrastructure of what is going to be running here. The first one is two Ethereum ledgers. So I'm going to just start up to Besu nodes and a signer for us. Then previously, I set up 3 Corda nodes. I deployed a Corda app, and I run the nodes. And I started up a server to talk to node A, started up a server to talk to node B. There is a Corda decoder or a proof generator that's going to generate some Corda proofs for us. And then there's some setup necessary. So the protocol that's in play here is given by the EEA. So it's a cross-chain messaging protocol. And there are some, or whoever is going to be the one that we trust, which is the validators on Ethereum Ledger, needs to be onboarded onto the other chain, because the cryptographic proof that they're going to get is going to contain signatures from these entities. So I'm just going to start the setup. There are 4 contracts, Ethereum contracts, that will be deployed on both chains. And the EEA spec structured them into 3 layers. We have an application layer that has your business logic. This will be our cross-chain XVP contract. Then you have a function call layer, which will be responsible for doing remote function calls through this messaging protocol. Then the messaging layer will be responsible for verifying your cryptographic proofs. And then we have a watered down asset token with just minimal functionality in Harmonia. The token contract, you can create holds like Treat said. You can make the hold perpetual, meaning it won't expire. You can execute the hold and you can cancel the hold. So that's simply your 4 contracts that resides on both chains. There's other things like we would set the validator list for Ethereum to Ethereum. So chain A's validator list will be onboarded onto chain B and vice versa. For Corda, we will onboard the participants as part of the consensus process. So this will be a notary, and in this specific case, the 2 participants of the transaction, which will be Bank A and Bank B. There are some other authentication parameters and things I'm not going to go into that also needs to be onboarded. Then I'm going to run the integration test in Harmonia lab that I'm going to demo from. So you going to see lots of logs, but I'll step through them as I go through the flows. So the first thing that we're going to do, as Pete said, this was already agreed on, that there is going to be settlement. The trade was already agreed. A unique ID was agreed on. So Bank A and Bank B on their respective ledgers will go place a hold, and they will make the hold or mark our application layer contract, our PVP contract, as notary, meaning that that contract can execute the hold. So on the other side, you will have the same. Bank B or Bob will go place a hold for funds on hold for Alice or for Bank A and mark the contract as notary. So I'm just going to go up to where we're running these things. So what happened here is we're going through an Ethereum interop service here to place the hold. This is not in the flows because it is not necessary. Nothing prevents Bank A from going straight to the smart contract and placing a hold. So here you will see it goes through our service to create a hold. You will get your receipt to create a hold. You will make the hold perpetual. You will get a receipt for that. Then you will place the other hold on the other GBP ledger. Receipt. You will make it perpetual. And then you will submit a settlement instruction. Again, this is not shown on the flows because it's for convenience and there's extra tests or checks that we put in. For example, before we do the smart check contract call, we will first check that both of these holds are in place. This is more for, you almost say, fail fast, that we don't go and fail on chain. But again, we cannot rely on the interop service because nothing prevents Bank A from starting the lead leg straight on the smart contract. So the settlement instruction will get submitted here. And this is just state changes inside the interop service. And eventually it will call start lead leg in the contract and it will get a receipt for it. So what does start lead leg do? Now we follow a leader-follower approach here, building on top of the cross-chain messaging protocol that these 2 layers are going to talk to each other. Something will happen on your first ledger, your lead ledger. We start a lead leg. It will be followed up on your follow ledger and it will be finalized on your lead ledger again. So the lead leg inside our smart contracts, blue is here our application layer, green is our function call layer, and pink will be our messaging layer. So our application layer, PVP contract, it will check whether there's been a cancellation against the trade ID. We will get the cancellations later where this will make sense. It will check that everything is in place for the hold. And then it will emit an event. Now, this is at the core of the cross-chain messaging protocol. This is the event that we will prove that happened on this ledger. And inside this event, we will wrap up the function that we want to go call on the other chain. So for this case, we want to go call request follow leg in a PVP contract on the other chain. The event will get emitted and the interop service will pick up this event and it will bolt a cryptographic proof, a Merkle-Patricia proof around it, proving that this event happened, and it is sealed with the validator signatures. This is nothing new. This is what Ethereum does in its block headers, or how it handles its storage automatically. And then it will do a cross-chain call. It will perform call from remote chain to the other chain. It will give it a proof, and it will give it this event that wraps an instruction. So maybe it just go in here to there. So the lead leg started. An event was emitted, and we know that this event will only be emitted under specific conditions that runs in smart contracts, and we will only accept this from authenticated contracts on our other ledger. So this is the event that was emitted. We would check some authentication thingies. We will build a proof, and we will do the perform call with quite a big proof. We'll get a receipt that it went through. So what does this mean when it was successful? So on the other side, the cross-chain function call layer will receive the proof and the event. It will decode it. And when we onboard it, we onboard different decoding schemes and verification schemes in our different layers. So for this specific chain, chain A, we will know there is only one decoding scheme onboarded, and we will use it. And we will pass it on to the messaging contract, which will have only one verification scheme for that chain. And once the proof is verified and it can go through, it will call this remote function using the data that was wrapped inside the event that we proved did happen. So request follow leg is then our application layer contract. We'll check for cancellations, check that the hold does exist and everything is in order. And then we'll execute the hold, transferring funds from bank A to bank B on ledger B. And then to prove this again to our other ledger, it will emit an event, and inside hold an instruction that it wants to go call on the lead ledger again, a complete lead leg. So maybe just go to where the event gets emitted again. We did a perform call, everything like this was executed, event was emitted. The event will be caught by the interop service. It will handle it, will create a proof now on the GBP chain, and it will perform a call across again back to the lead ledger, where the same thing will happen. You will have a certain decoding scheme registered, and you will decode the event. You will verify the proof that came with it. If everything is okay, it will execute the function that was wrapped inside this event. This will be complete lead leg. And the complete lead leg will then execute the hold on the lead ledger. And this will be the happy path for PvP. And just to follow through on the test that you see here, the perform call from remote chain, you got your receipt. And the test here, if you go and run it for yourself in your Harmonia lab, you will see that the amounts and everything is checked again. So then if we have to come to another scenario for cancellations, rule books say that there cannot be a case where only one of these legs go through. Either both of them has to go through or both of them has to be cancelled. And this brings us to cancellations. You must be able to, under certain circumstances, go and cancel your hold. So to avoid race conditions to make all of these cases work, we in the rule books, we said that you cannot go and cancel on your own ledger unless there's already a trade marked as cancelled. So you will have to go, if you want to cancel your own hold on chain A, you have to go through chain B. So when will we want to cancel? In this case, suppose bank A does everything, he places his hold, and bank A could even start the lead leg where Bob did not place its hold, or bank B did not place a hold. The start lead leg will fail. So this is not indicated here, but suppose that did happen, or it didn't even happen. Alice realized she waited enough time for Bob not to place its hold. So she wants to start cancellation, and now on the follow ledger. So this goes through our interop service again to start the cancellation, but nothing prevents you to go straight to the contracts. So this is the next test here, where you will create the hold only on one side. You will get a response, make the hold perpetual, you'll get your receipt, and you will initiate a settlement instruction and say that it must be used for cancellation. And here it will eventually send the start cancellation instruction to the smart contract. What does start cancellation do? It checks that the hold does not exist in the smart contract, and then it marks the trade as cancelled against the trade ID. And then to prove this, it will emit an event, and with it wrap inside again a function that we want to go call on our own home ledger or chain A, and this will be perform cancellation. So the event will go again, be picked up by the interop service, a proof will be built around it, and it will be used to perform a call from remote chain. The function call layer will decode, messaging contract will verify, and you will eventually call your perform cancellation function on chain A. And perform cancellation will then check if this is a direct cancellation or a cross-chain cancellation. Cross-chain, this means it comes with a proof. There's two options here. And then it will mark the trade also on chain A as cancelled. Check if the trade is cancelable, and then it will cancel the hold. And this is just the event for our API service or our interop service to know that the flow is now complete. So if you want to know about the other case here, when is it possible to go cancel on a hold on my own ledger? So suppose now after all of this happened, Bank B go and place this hold. And he must be able to cancel this hold again without having to go through the other ledger, because that process already went through on its ledger. And for that, we know that a trade was already marked as cancelled here. So in that case, we allow Bank B to directly cancel its hold because there was that trade that was marked as cancelled. And then it will cancel the hold that was placed afterwards and just emit an event that our interop services will know what to do. So, but you can just follow through here. You will start cancellation. An event will get emitted. Proof will be built around it. We will perform call from remote chain, and it'll be the end of the flow. Amounts will be checked inside the test, of course. So I'm not going to go through the other option here for PVP cancellation. It's exactly the same because it's two Ethereum ledgers. So this is the case where Bank A does not place its hold and Bank B wants to cancel. Bank B has to go to chain A, generate an event that we can get a proof from that this trade was actually marked as cancelled on your chain A. And then Bank B will be able to cancel its hold. And the same scenario, if Alice would come and place a hold afterwards, she must be able to directly cancel her hold. And she can do that because the trade was already cancelled. The trade ID was already cancelled against in a previous flow. So that's your PVP flows. I'm next going to go to the DVP ones, which is probably the one that's more interesting with the Corda chain. Is there any questions so far?
I think the team has been doing a fantastic job of answering questions while you're presenting, Marilyse. This is
great.
Really?
Okay, awesome. Awesome.
But if you have a question for Marilyse, please in chat, let us know.
So Corda works a little bit different. State is not updated like on Ethereum. You will create a new state if you want to update, consuming the previous one, and it can only be consumed once. So our example here is driven by our use case with HKLX. They work with digital collateral records. It's pretty much a basket with securities that it's issued by an issuer, and you can transfer it to another owner. For HKLX, we had to drive sort of the whole earmark flow into them to be able to earmark the basket of securities before we transfer it, that it can fit into our flows. And for the flows here, we already assume, but I will show in the test that I have to create them anyway. We assume that there's already this DCR basket of securities created on the Corda ledger. And there's already a trade created, which is a different state, and it has a different Corda contract to verify. This state was needed for cancellations mainly, and I will get to that later. So it will be the same principle on the right-hand side for Ethereum. Bank B will place a hold, placing holds, or let's call it, I think it's pounds in the example here. on hold for Bank A. And then on the Corda side, a draft transaction will be created to now mark this issued DCR basket, earmark it for another bank, for Bank B. And if you think of Corda, your input state will then be this available basket. It will consume it, and the output state will be an earmarked basket. And Bob will, very importantly, validate this because we don't have validating notaries. And it will sign it, and the notary will then attest that it's unique inputs. So at this point in time, we have a transaction in both Bank A and Bank B's vault and Corda. And we don't have a concept of an event that we have in Ethereum. So it's not directly translatable. So we're going to use the best thing we have is this transaction, this signed transaction that we're going to rip off the Corda ledger, and we're going to wrap a proof, turn it into a Merkle proof. So before we start the lead leg, which is not an Ethereum function, we technically wanted the Corda side here to bolt the Merkle proof out of the Corda transaction, but our use case with HQLX demanded otherwise. We built it into our interop service, that it will create a Corda proof from a signed Corda transaction, a raw signed Corda transaction. And this is why we needed that decoder or proof generator running separately. So from the transaction, it will submit a settlement instruction and with a raw transaction, which will then build a proof and do the perform call from remote chain, which we previously did with an event and Ethereum Merkle Patricia proof. Now we're doing it with a Corda transaction and a Corda Merkle proof. And the same will go through. There's a Corda decoding scheme and a Corda verification scheme that is registered on the Ethereum ledger. So it will know how to decode this and verify the Corda proof. And it will call the request follow leg as before, which will execute the hold on the Ethereum ledger and emit an event, wrap within it an instruction to complete the lead leg on the Corda ledger. Now, this is exactly the same as if there was a smart contract function existing on the other ledger, which there is not for Corda. But ideally, one would like to be driven by this, and the Corda flows should be equivalent to a complete lead leg. So a Ethereum proof will now be built for this event, and it will use a callback because it's like how our use case with HQLX was. They would submit a raw transaction to us with a settlement instruction and give a callback for us for a proof because we had to build a proof for them. And also because the Ethereum nodes was not exposed to HQLX. So via the callback instruction, a Corda service here will now initiate the Corda flow to perform, to confirm the DCR flow. So this is essentially transferring this earmarked DCR to a transferred DCR. And very important here, Alice will verify the Ethereum proof before anything else in the Corda app, before anything else proceeds. Create a draft transaction that will now take two inputs. It will take the XP, consume the XVP or the DVP state, which is a created state, and the earmarked DCR, and output just the transferred DCR. Bob will validate and sign, or Bank B, and the notary will attest that it's unique inputs. And that is the end of a happy flow from Corda as a lead ledger and Ethereum as a follow ledger. And then obviously we need to deal again with cancellations. What happens if one party does not place a hold, for example. So, I have to go through the demo here. Sorry, I should have skipped to it a little bit sooner. So what happens first, we create a hold on the Ethereum ledger. We make it perpetual. And then we create a hold on the lead ledger. Now, like I said before, because it's a test here for every case, I'm going to create a basket. I'm going to create the trade on the Corda ledger. And then important, the one that we were going to prove is the earmarking of this DCR basket. This is the Corda transaction. And then it will receive a settlement instruction with this raw transaction. It will call the decoder service or the proof generator service to build us a Merkle proof from this Corda transaction. And then it will perform call from remote chain with a rather large proof. We get a receipt back. it was verified successfully. And then an event will get emitted as before on the Ethereum chain. Interop service will wrap it into a proof and send it on via callback to the Corda flow, which is now the output of the Corda flow that would have taken the state to transfer it. And here the proof is part of the state. And that's the end of the happy path flow. We can again check balances, but that is all in the test if you want to run the Harmonia test yourself. So then to come to cancellations, which is different from Ethereum. I'm also going to run just through one because it's the same on the other side. So what happens, like Corda earmark successfully its basket, but Bank B on Ethereum does not place its hold. So Alice would start cancellation. First, maybe start lead leg by submitting the settlement instruction, and it will fail on chain. So what would you do then to cancel her earmark on her basket of securities? She has to go through the Ethereum ledger. So she will start cancellation, which will initiate a function on a smart contract that will emit an event that we're going to prove that this trade is now marked cancelled on the Ethereum ledger. This event will be used as proof. So we wrap it in a Merkle Patricia proof and we pass it back to the Corda side via a callback. And then the cancellation flow will kick off on Corda. Again, Alice or Bank A will have to verify the Ethereum proof and check or create a draft transaction cancelling her hold. What will be the input? You'll have an earmark DCR. And then you'll have your XVP state that's not cancelled yet. You will consume it in its created state, and you will take your DCR state back to available. This is equivalent to an Ethereum side of cancelling your hold. And then if Bob comes afterwards and places a hold on the Ethereum side, he can, as before, cancel directly because there's already a trade, or there was already a cancellation against that trade ID. What happens? Go back to the both earmarks in place. This is the one where the Ethereum trademark is not. This is the one I just spoke through. So we will create a basket, we will create a trade, we will earmark the trade on the Corda side, send the settlement instruction, or the cancellation instruction to cancel the hold. It will record the callback, start cancellation on the Ethereum ledger, start cancellation function, you get a receipt. It will emit an event, we will wrap it in a proof. It will be sent via callback to the Corda side, and your basket will be taken back to available status. And then you can check your balances again. So on the last case then is if the Ethereum side places a hold, but not the Corda side. So Bob wants to cancel his, or Bank B wants to cancel his trade. He has to go through the other ledger. So it will initiate a flow, a Corda flow, to cancel the trade. And it will use that as proof to, and provide it to the Ethereum ledger. So what does cancellation of a trade entails? It's a flow that will take in, consume the XVP state and create it, and the output state will be a cancelled XVP state. So this is again a Corda transaction that we pass on raw to an interop service that wraps it into a proof, into a Corda proof. We perform the call from remote chain to the Ethereum ledger. The Corda proof gets verified, and we perform cancellation on the Ethereum side. Then the trade will be marked as cancelled. The hold will be cancelled, and this is just for our interop service to know that it's now complete. And the same happens on the other side. If Alice comes afterwards on Corda and places an earmark, she wants to be able to cancel it directly in this special case that there was already a cancellation. So how would this work? You will consume the DCR state that should be an earmark. There should be a earmark, and there's a cancellation XVP state in cancel state that you will consume, and it will take your DCR state back to unavailable. And that is it. for our demo. I don't think there's any other cases that's useful. No. Okay, is there any questions? Or did someone do a very good job again to answer them?
We were trying to answer in the chat.
Okay, awesome.
Great. I think thanks very much, Marlies, for taking us through that. Just to say, if you didn't catch it, almost all of that code is available in Harmonia. There's just one piece that we will be contributing over the next couple of weeks, which is the signer, which obviously you need to sign the transactions. But everything else is there. All the documentation is there. So please feel free to jump in and have a look and read through. We've tried to make it as kind of easy enough to follow, but comprehensive enough that we cover, everything that's in there. So there's a huge amount. It's many years of work actually that's gone into it. So and we'd love to get some feedback and some views on it, and improve it as we go. All right, I'm going to hand over to Dominic to carry on with his presentation.
Okay, super. So I'm going to share my screen in a moment. This will be a fairly short presentation. Basically, I'm going to step through a cross-chain swap from the Corda side using the code that mainly Eduardo has contributed. And I'll talk a little bit as I go about what it is that I'm showing. So, just share screen. And yes, do and there. If it's working. If that doesn't work, I might have to drop out and come back in. That's great. Okay, that's better. So that is right. So hopefully everybody can see my IDE. So what we have here is a single JUnit test. And what we're doing is we're running up a mock Corda network. This saves me having to deploy a bunch of Corda nodes and send RPC messages to them so they come up from the command line. Instead of that, essentially what we'll see is quite a lot of things where we have an identified Corda identity running a flow with a given name, and that's how I'm going to drive the sequence of events here. So what I'm going to show is a sequence of Corda flows being executed that cause various things to happen, and the sum of those things will be the atomic swap, all of it driven from the Corda side by the Corda flow framework. So the preamble, we have 4 identities in this picture. There's Alice, who holds tokens in an ERC20 contract on the EVM network and wants to use them to purchase an asset on the Corda network. And we have Bob, who holds the asset to be purchased. And there are 2 other characters sort of hanging around on the periphery of the scene, which is Charlie and Dave, who are acting as trusted relays attesting to the finality of transactions on each network. Now, the reason that they're involved is that when Eduardo was first designing this code and then implementing it, the scope was effectively all possible kind of EVM-based Ethereum platforms. So not only those which have deterministic finality, where there's a known pool of validators whose signatures you can poll to see if something's been finalized, but also potentially things like Ethereum mainnet, where determining whether a block is finalized in a way that you can do a check offline is a much more complicated business. And also, it wasn't entirely clear whether we had a way to check Corda signatures, which use a different signing scheme to Ethereum's, on the Ethereum virtual machine. So on both sides, what we have is witnesses who will basically say, I have seen this Corda signature on this thing, and here is my EVM readable signature to say that I have seen it. and on the basis that these witnesses are trusted on each side, that's how we kind of establish finality. This isn't necessarily the mechanism, and this isn't the mechanism that the Zadara's implementation uses at all, because they have the ability to check and prove finality in different ways. But this is a kind of a general purpose fallback mechanism for if those approaches sort of fail you. So this does also illustrate the process whereby we send out for signatures and get them and present them as evidence of finality. And I'll talk a little bit more in a moment about how that kind of fits into the general framework of proof we're using. The other character is the notary, which is a standard component of a Corda network. It signs transactions on the Corda network, but it signs them using a non-EVM native signature scheme. For those who aren't so familiar with Corda, it's basically a UTXO ledger, which means that every transaction produces output states potentially and consumes the output states produced by other transactions. And the notary's job is to observe for any given transaction whether the output states it's consuming have been consumed by any other transaction, and to forbid the transaction if they have. So it's only really there to prevent double spends. The transaction data is formatted as a Merkle tree, and everything other than the hashes of the input states is torn off. So the notary doesn't actually see the details of the transaction, it just sees what states are being consumed in it. So notaries are not validating as well. This is a noticeable difference from the Ethereum model, obviously, where your validators run the transaction code. So each of Alice, Bob, Charlie, and Dave has an identity on the Corda network, which we write as Alice at Corda, Bob at Corda, and so on, and a wallet stroke signing key on the EVM network, which we write as Alice at EVM, Bob at EVM, and so on. And I'll just take a quick look at the testnet setup here. You can see that these are currently hard-coded into the tests. So we've got Ethereum addresses for Alice, Bob, Charlie, and Dave. We also have private keys for signing with, and we've got some addresses. We've got the address of the deployer. We've got protocol address, which actually is the address for contracts called Swap Vault. And we've got gold token and silver token deploy address, which are addresses of ERC20 based tokens, very basic things. They have total supply balances, the ability to transfer things, and importantly, the ability to allocate a portion of your balance to another account to act with on your behalf, which is something that's used here. You can also see we have a mock network set up and some mock nodes. So essentially, we're kind of running a Corda network in a box, which is what we'll be using to run through this sequence of actions. Okay, so given that so all of the actions in the swap are taken by running Corda flows, and some of these create, distribute, and finalize transactions on the Corda network. Some of them use the signing key for the corresponding EVM wallets to propose transactions to the EVM network. So sometimes Bob at Corda will run a flow that basically says, using the signing key of Bob at EVM, sign a transaction that does this. Obviously, in a real production environment, you probably wouldn't have your Corda node holding the signing key for your Ethereum wallet. There would be some kind of audited proxy or relay through which you did perform that action. You don't want to kind of combine those kinds of authority in one place. Given that, the other things that the flows do is they obtain attestations from Charlie and Dave. So given that Alice and Bob have already agreed to make the swap, the sequence of actions, it runs like this. First of all, Bob drafts a Corda transaction. So in Corda, you can create, every transaction is effectively a Java object with a bunch of different pieces of data attached to it. And you can create one, you can serialize it, you can obtain the hash of it without actually performing that transaction or notarizing it. And you can do so knowing that if you later on do sign and notarize the transaction, it will have the same hash. So this enables us to draft a transaction, as Bob does, and send it over to another party to verify, to say, does this do what you want? Does this give you the benefit that you're seeking from the swap? So Bob drafts a Corda transaction, which, if it's signed by him and the notary, will transfer ownership of the asset to Alice. Alice verifies that that draft transaction delivers the benefit she wants, and then commits tokens on the EVM network. And that's there are two steps involved in that. First of all, Alice at EVM uses the ERC20 allowance function to allocate the tokens to an allowance held by the swap vault contract. So the swap vault contract can then act on those tokens. And secondly, Alice at EVM uses the swap vault contract, which uses the commit with token functions to transfer that allowance to the contract itself, simultaneously setting up a commit state which records the conditions under which the tokens can then either be returned to Alice or transferred on to Bob. So at this point, the contract holds some balance and has the ability either to return it whence it came or forward it on to the intended recipient. Bob at Corda then goes ahead and signs and notarizes the draft transaction, and then collects EVM checkable signatures on the draft transaction hash from Charlie and Dave, attesting that they have observed and validated the notary's signature, that the notary's signature on the transaction hash is valid. So if you have the ability to check all the signatures on the EVM side, you don't need this bit. And in fact, in Adara's implementation, there is some code that does just that. But it's, again, if you're working with a platform that just can't read Corda notary signatures, you have to present it with some evidence from somebody that the transaction is finalized. The next step is that Bob transfers the tokens to himself using the transfer function on swap vault, presenting these signatures. So at this point, the swap vault contract basically says, if you can show me signatures on this transaction hash, you can have these tokens. And importantly, when this happens, the transfer function records an event into the transaction receipt for that transaction, and we can show a proof that that event appears within the receipt appears within the receipt storage for the transaction block, and that's how we kind of construct a proof readable on the Corda side that the transfer has taken place. Now, Alice needs proof that this transaction has been finalized. And again, where your EVM platform has deterministic finality, where you've got a set of validators whose signatures you can check, that's quite easy to do. But in circumstances where it isn't, essentially we say, again, to Charlie and Dave, who are on hand to attest to things, can you check that these blocks have been finalized and signed to say that you've observed that they have? And then you basically trust Charlie and Dave's signatures in that matter. So Alice at Corda collects those signatures from Charlie and Dave on the block hash, basically saying, yes, we've observed that this is finalized in the EVM network. And finally, Alice at Corda runs the unlock asset flow, which uses those signatures together with the Merkle procession inclusion proof to show that transfer took place and that it was finalized. And that satisfies the Corda contract verification rules for unlocking ownership of the Corda assets itself. So let's kind of step through this, and I'm actually going to start running in debug. Let's do it here. So the first thing we do is, in this test, is we just create a random ID for an asset, and we run issue generic asset flow, which literally just creates a Corda state representing the asset that Bob holds. And then we have two further preparation steps. So we create, rather than the event itself, we create an expectation. In other words, we kind of capture the properties of the event that we expect to observe. We expect to observe that a given amount, in this case 1 token, is going to be transferred from Alice to Bob against the gold token. And also we expect that Charlie and Dave will have been the signers involved in authorizing that to happen. We can't actually build the event itself yet, because the event is going to include a reference to the draft transaction hash, and we don't have that because we haven't created the draft transaction. There's an interesting kind of circuit here where one thing depends on the other, but we can't have them form a cycle of dependencies. So we're going to pass this swap vault event encoder into the draft transaction, but it obviously can't know yet what the draft transaction hash is, so it can't make reference to that data yet. And the draft transaction, basically, so Bob now runs a flow that says draft the asset swap flow, Here are the transaction hash and state index of the asset that we want to transfer, which is the state emitted by the issuance we did earlier. We're going to transfer it to Alice, and this is the notary that's going to notarize it. Here are the parties that are going to witness the notary signature and sign it with an EVM readable signature. And we have a signature threshold, so they both have to sign. We could have a larger pool of witnesses and do a sort of N of M thing where you say 5 out of these 6 or 5 out of these 7 need to sign. And we pass in the swap vault event encoder, basically saying if you can show an event that matches what this will spit out when given the hash of this transaction, then you can have the asset. Okay, so we have reached this point and we've done a print balances. So we're just looking at what the balances held by Alice and Bob and the protocol before the commit are. And that should be visible. Is it on the whole thing? That will be debug. Here's what it's specified. We'll look at those at the check that out at the end and we'll finish running. So the next step is that Alice commits her tokens to protocol contract. So Alice runs a flow, commit the token flow. I'm just going to show you that fairly quickly. What that actually does when it's run is it uses the EVM interop service provided by Corda. And what we've got here is we're using Web3j. We've got a wrap around the swap vault contract and the ERC20 contract. So the first thing we do is run an approval, basically saying that we approve this amount to the contract address. And then we do commit with token on the swap vault, which basically takes the money using that approval and creates the commitment that would then enable it to be moved back or forth depending on the conditions that are met. And you can see that the commitment records the signers that we want to see, the signature thresholds, who would receive the money if everything was in order, and what the amount is. Okay, so going back to swap demo. We can move on. Review. No, I don't want to rerun it. The wrong button. Never mind. We'll come back to there in a moment. Fortunately, each one of these can start with a fresh asset, so we don't kind of trip over ourselves. Put the setup time there as running. Let's see if anybody's got any questions while that's into. Okay, the question about the relays is essentially the important thing here is that once Alice has transferred funds to Bob, or rather once Bob has taken the funds from the commitment made by Alice, Alice then has to be able to obtain the asset from Bob without Bob's further intervention. So purely by showing a proof that this has happened, I can get the thing. Otherwise, you'd be in a situation where Bob has taken the funds and Alice says, okay, well, you now approve my having the assets, and Bob vanishes or does not cooperate, and we're in a sort of a stuck state. So what we want is the ability for Alice in obtaining the assets to act without further involvement from Bob, purely representing proof. And because the proof involves not only proof that a given transaction has certain properties, but also proof of finality, we need Charlie and Dave effectively to provide that proof of finality. And that's true, as I say, only in the case where we don't have deterministic finality, where we can't just sort of check some signatures on the block hash ourselves. Okay, so going back to here, what we want to do is run forward. So once the commitments has run, that's when Bob signs and notarizes the draft transaction. So we see that the money is in a committed state. So by signing the draft transaction, we create a situation where Alice can automatically obtain the asset if she can show that Bob has taken money. And Bob also grabs the signatures from Charlie and Dave attesting that the draft transaction is notarized, because Bob needs to show that that lock has been set up in that way in order to take the money. So once we reach this point, Bob runs claim commitment with signature and basically says, I would now like the tokens that were committed. Here are the signatures that show that I have notarized the transaction that places the Corda asset such that Alice can claim it if I've taken the cash. Once that's gone through, the next step is for Alice to in turn collect signatures showing that the transfer has occurred. And then use them with unlock asset flow to obtain the asset for herself. Look forward to that point. What would take the place of this in the case where we had deterministic finality is that Alice would simply observe the signatures on the block hash itself of the validators on the EVM side and use those instead. So we're using these witnesses, as I say, as a substitute for that. Okay, so unlock asset flow unlocks and finalizes the transfers to the recipient by producing and presenting proofs that the EVM tokens were transferred to the expected recipient. You took the money, therefore I can have the assets. And at this point, you can't stop me, essentially, provided I can show proof that that happened. Not what I want to do. That one. We run forwards to the ends, and we have a couple of assertions to make sure that things have ended up in the state we expected. So we verify that the unlocked assets are now owned by Alice, and we can do that by taking the transaction that comes out of unlocked asset flow and show that it has an output state, which is an ownable state whose owner is Alice. And we also show that Bob, querying his vault to see what assets he holds, no longer holds that asset, so we can prove that the transfer of the assets has occurred. So once we have, when we come to the end here, let's see if I can actually find the outputs and the print balances, just to show the movements of tokens between accounts as this goes on as well. See how that's been set up with its kind of creating this mock Corda network here. Yeah. So balances before commit. Alice has some vast number with 1 on the end. Bob has some vast number with 9 on the end, and the protocol holds nothing. Balances after commit, that 1 has gone down to 0. And Bob's 9 is still at 9, but the protocol now holds 1 token. And then the balances after transfer, so that Alice is still down to 0. Bob's 9 has gone up to 10, and the protocol doesn't hold it. So effectively, there's a brief moment where the protocol holds the balance, so it holds the token, and then it gets transferred on to Bob in this case. So there are also tests, which I'm not going to get into now, because I want to keep this fairly short. But the commit claim swap test, and this is all in the repository, you can see various other paths, including the unhappy paths shown where, for example, Bob can revert Alice's commitment. And by presenting proof of that reversion, can get his asset back. So there are kind of paths, ways to back out of the lock on both sides, and that's all kind of illustrated by the other tests here. But I just wanted to kind of run through the main example. Okay, so that's it for my demo. Mercifully short, I hope. If anyone's got any questions, I'm happy to take them now.
We do have a question in chat. Thank you for that, Dominic. We do have a question in chat. If both Alice and Bob have accounts and can initiate transaction flows on both EVM and Corda, why are the relays Charlie and Dave needed? Could Alice and Bob do the checks and gather the proofs themselves, but the relays just provide a convenient service so they don't have to handle that part?
Yeah, so by calling them relays is actually a bit confusing in this context, because obviously, particularly in a Cacti scenario, a relay is something involved in kind of getting information across from one network to another. In the working paper in Harmonia, we call them witnesses, which may be a better name for it. Their job is effectively to attest in a form that one network can consume that something has been finalized on the other. So underlying all of this is proof of action. Effectively, what we want to do is construct conditions on each network that say this can only be done if you can show proof that some reciprocating action has been carried out on the other network. And proof of action breaks down into two parts. One part is what I call proof of outcome. In other words, proof that a given transaction did the thing that you want. And the other is proof of finality, which is basically evidence that that transaction is recognized by that network as valid and final. And with the all of the proof of action is done by, on the EVM side, looking at events written into the event logs or the transaction receipt and constructing your Patricia-Merkle inclusion proofs right the way up to the block hash. On the Corda side, we can't do that. It's very difficult to make a kind of a Corda transaction externally legible. And so what we do is we have the recipient of the benefit of the transaction validate the draft transaction and basically sign to say, yes, I agree, this does what I want and I will get the benefit I'm looking for out of it. But those are only the proof of outcome parts. For the proof of finality, you need some way of checking finality on a remote network. And you need to be able to do so without being online in that network, without having to kind of go away and ask it, because the smart contract validation obviously has to be deterministic, and typically, it's offline. Effectively, really, you just want to be checking some signatures or some other kind of evidence of the cryptographic integrity of something you've been given. So, one way or another, we need to provide a verifiable evidence of finality. If you can read Corda signatures, then the Corda notary signature on a transaction hash is proof that that transaction is final on the Corda network. If your EVM network is using a quorum of sort of fixed validator pool, and you can again say, okay, these people have signed it, therefore it's final. But if it's something like Ethereum mainnet, it's quite a lot more difficult to establish finality in a way that's kind of offline checkable. So the witnesses on both sides in this example are basically there to say, in the event that you can't read Corda signatures, so you can't tell whether a notary's signature on a draft transaction is valid or not, and in the event that you can't easily prove finality on the Ethereum side, you can take the signatures of these witnesses as evidence. They are assumed to be kind of parties who are uninterested in the outcome of this particular transaction, where they're kind of just mutually saying, yep, that definitely happened on my network. And that's how you kind of complete the proof of action by using them to provide the proof of finality. Does that clear that up?
That's great, Dominic. Thank you. And thank you to Jerry for asking that question. We've got a question from Jim. So the Harmonia agents on each platform communicate to each other to coordinate the transfer process with proofs. What is the protocol the two agents use to communicate with each?
So in the example I've just shown, which works quite differently from Adara's, and I might kind of call Peter or Marlies back in to kind of answer from their side. In the Corda case, every identity in the Corda network has its own node within a permissions network, and they send messages to each other via a peer-to-peer messaging layer. So the way that they communicate within Corda, so Bob's talking to Alice, Alice talking to Bob, is via that peer-to-peer messaging within the Corda network. The way they talk across networks, so the way that Bob at Corda instructs Bob at EVM to do something, is through in this case, it's through a Corda service that just directly makes Ethereum RPC calls against an Ethereum client. And that's where the Web3j magic allows us to just find the example of flow that does this. No, we do actually. So, for example, in print balances, we have a get balance flow, and what that does is it just obtains the EVM interop service, grabs the ERC provider for the given token address, and just calls balance of. So we are literally making an RPC call across to the other networks to get information back, also propose a transaction or whatever. Commit with token flow, it's the same. When we actually run it, we've got the provider for the swap contract and the provider for the ERC20 contract. So the Corda flow here is basically saying, I am Bob at Corda, and as Bob at EVM, I would like to approve this amount to this contract address, and then I would like to instruct this contract to create the commitment. And so that's just plain, it's actually kind of JSON over HTTPS.
Awesome, thank you. Can anyone from the Harmonia team help out with that one as well? All right, so Peter just said we simply use an HTTP API call in the Adara example. In the real world, as Dominic has mentioned, it's an internal bank communication. So that's great. Thank you both for that. Jim, I hope that helped. If you do have a question, please put it in chat.
Yeah, so maybe just to clarify, that'll use whatever infrastructure the banks have. So it could be queue infrastructure, could be something that's based in their Kubernetes environment, could be MTLS type connection. So we've seen a number of different protocols used for bank-to-bank communication or component-to-component communication within banks, service mesh type thing. So that's typically how it gets done, but it's obviously locked down within the bank's infrastructure.
Okay, so I will stop sharing my screen at this point.
I think it's back to Peter.
Okay. Thank you, Dominic. Thank you, Peter. Thank you, Malaise, for the demos and the great explanations. I will build on everything that has been just said, and I will show how you can work with contracts, smart contracts, such as the ones that were being demoed right now, within the confines of the framework. And to get started with that, I've created a little list of steps that you can take to try and follow along at home. Now, 99% of the time, these steps don't work on other people's computers. It's because it's impossible to predict all the operating system level dependencies that could be missing or incompatibilities with the operating system itself, or other kinds of issues like when you don't have enough memory in your machine. But nevertheless, I'll explain through each step, I'll show it, and I'll demo it working as well, hopefully, if the demo deities are with us. So I put a link in the chat that takes you to the README file of the workshop demo. And it's sort of a high level list of steps to execute. But if anyone has any questions, I'm here. And also, I wanted to highlight once again that we have daily pair programming calls where you can drop by in the future if you have any questions or anything to clarify about all that. So with all that said, let me share my screen. Okay. So the first thing you do is clone both repositories. Now, if you look at the actual URL, then you'll see that it is my personal fork of both of these repositories, not the upstream repositories. And the reason for that is because I've had to make some changes to make the demos work. And the first mistake I made is that step 5 should be executed only later. So the first thing to do is to clone the repositories and then move on to step 7. And we'll get back to step 5. So I've already cloned all of these repositories and everything is kind of set up on my side. So I will get on with actually showing off the pieces. So one thing that I needed to do on my fork is to alter the migration script for one of these contracts. Within the Harmonia lab, there was this R3 Atomic Swap folder, and that has the EVM interrupt workflows. And so as I was trying to deploy it, I was working with the main branch of the lab, the upstream repository, and that did not have this migration script, so I had to add this. So if you check out my branch on my fork, then this is an extra thing that you get. This is what makes the contract deployment functional. And I just wanted to highlight this because in the spirit of collaboration, I'm planning on sending a pull request to the Harmonia lab, and we can talk about that more later. All right. So I'll show you the build working in the Harmonia subfolder. So you have to change directories, come down into the Corda directory, and then you have to run the Gradle build. And now the tests right now are not passing, so you just have to do the build. And what will happen then is that you will end up with this build folder that has a libs folder that has your jar file, which contains the workflows. And the same way, there will be a jar file in the contracts folder and also in the common folder. And so the way Cacti helps you, one of the ways it helps you is that we ship an all-in-one container image for all the supported ledgers. In our case, Besu and Corda, just for the scope of this workshop. And you can deploy these jar files to a running Corda ledger that is running within the container, just from these jar files. by sending them through a REST API endpoint. Now I have to highlight the REST API endpoint for deploying contracts as strictly for development only. You shouldn't use that in production because certain shortcuts had to be taken in order to make it much more convenient to use. But this also means that if you were deploying your contracts into production with that endpoint, it would not be considered safe to do that. So after that, we can go over to the steps. So yeah, I showed you how to build, and then I left some steps here on how to deploy contracts to the Besu ledger as well. This is mostly just an extract from what's in the README of the Harmonia lab already, but there's one slight change. If you see here, the network is specified as Cacti. So what that does is that if you look at the file under EVM hardhat config.js, then you will see here that I've added this little snippet. These are all accounts that are the example accounts of the Besu Genesis file that they had as of version 1.52, I believe. And okay, no questions so far. Okay. Yes, so with this Cacti network, this is what you get. The all-in-one ledger gets pulled up on this RPC endpoint. And so when you specify on the command line that the network should be Cacti, then the tool will pick up this information and make sure that it gets deployed to the right ledger. And now continuing down the steps, you also have to build a Docker image. But first, you got to switch over to the Cacti repository. So what this does, it builds a more up-to-date version of the connector. This is also a necessary step only temporarily because I had to make some additional features in the connector in order to be able to support the demo itself. Specifically, the endpoint for querying the vault, the Corda vault, has been added. So now if you issue an asset the same way that Dominic was just demoing it, then with this new endpoint of the Cacti Corda connector, you can query the state of that asset and take a look at the data. So I will also show that Docker build is working. If I can, yes, I just have to paste it in here. And on my machine, this image has already been built, so all you see is the cache is getting accessed. So on your machine, it will take a few minutes because it's not exactly fast. And then after that, you can do a series of steps again, which is mainly just configuring the Cacti build. Install the dependencies, compile the code, specifically the TypeScript code. And then there's this build dev script that you also have to run. And right now that won't finish because there's a little issue with Webpack bundling of the JavaScript sources that I haven't had the time yet to fix. But that, luckily enough, only happens at the very end of the process. And all the other things, the things that we need from the build are actually already there by the time this failure happens. So you can just run the command and not worry about it not finishing all the way through. And then at this point, I will start the ledgers. So, well, actually, before I even do that, I will show the Docker files itself. So we have the Cacti API server. You can see here which exact image is being used. We always use versions that are pinned down to a very specific hash or release tag, because that way you get reproducible builds for the most part, meaning that the probability of this working on somebody else's machine at another time is much higher than if we used, for example, just latest. Because with that latest, what would happen is that it would always, not always, but every now and then it would give you a different version of the underlying image. And then we would run the risk of introducing incompatibilities, bugs, and then that would cause people headache. And so you can see here the environment variables are configured so that the authorization protocol is none. So again, this is just for demo purposes. Don't configure it this way in production, of course. And then here's the plugins list of the API server in a JSON document. I'm just highlighting this because one of the cool features of the API server is that you can declare plugins to be installed at runtime, and then you can deploy those as REST endpoints if the plugin itself supports it, and all of our connectors do. And then there's this other image called connector Corda JVM. What this does, this is an actual JVM or Java application that is responsible for interacting with the Corda ledger directly. Now, the reason we need this is because in our demo, we're using Corda 4, and Corda 4 does not allow you a very easy way to communicate with it directly from Node.js. So this is one of the value adds of the Cacti framework, is that if you deploy this connector, then you can use it to deploy contracts, and you can use it to invoke those contract flows, get a network map, query the ledger state, and similar things to that. And you can do all that through a REST API that this app exposes, so you don't have to run and develop your code in a JVM specific language if you want to work with Corda 4. In Corda 5, this will be much easier because I believe once Corda 5 is out, then that will allow you to communicate with it directly over HTTP. But for Corda 4, you need a utility like this unless you are already on a JVM-based project. Let me check for questions real quick.
Hey, Peter, we've got a question from Jim. For the architecture defined here in the demo, what security teams have signed off on the design so far? For example, the ability to dynamically install, load runtime plugins, etc.
There was a security audit for version 1.0 of Cacti, where we had this feature in the API server, and I don't remember the security audit company's name, unfortunately, but we got a sort of a grant, or I don't know what the right terminology for it is, but the foundation had acquired us this security audit that was done to great detail, and they signed off on it. But that's specific to the runtime dynamic plugin install. And so it's not specific to the Corda contract deployment, which is not signed off at all. That is not meant for production. And there's a spectrum there as well in terms of the dynamic plugin install, meaning that if you want to, you can lock it down in terms of the code that's being executed. Because if you want to, you can build your application in a way that the plugins that you are going to load into the API server are already pre-installed with the exact specific version of the source code of that plugin that you know is safe. So you can have those pre-installed, and then you can configure the API server in a way that it loads those local versions of the plugin without ever having to go over the internet and fetch something that may or may not be what you want. So there is a possibility for locking it down. That way you can pin the plugin code to a local version. And because of that, that's why I would say that you are able to achieve security with it. And then, of course, there's, even if you do a dynamic install anyway, and you just fetch whatever plugin you thought of directly from npmjs.com or the GitHub package registry, you still get the protections that are there in terms of if you have a package log file or a yarn.log file. Those will come with hashes of the dependencies that you're fetching. And so even then, even if you go with the quote unquote less secure version, you're still technically protected by some pretty strong crypto that makes sure that what you downloaded is what you wanted to download. But with all that said, if you want maximum security, then you can just pin it to local installations.
Yeah, and that was Jim's following up on the dynamic plugin feature. Can we lock the allowed versions to load so we don't accidentally add new / untested versions?
Yes, that's just something you can do in your package JSON itself. It's this is definitely my favorite question so far, just because it's one of my pet peeves, actually, that every dependency in every package JSON file and the Cacti project or any project where I do code reviews must be pinned to an exact version. Auto upgrades through the tilde and the caret specifiers are not allowed because of exactly this reason. If you allow auto upgrades of any dependency, someone could compromise the publishing process of that dependency and push a new release that's just a little patch or bug fix, as it is advertised as such. But what it actually does, it loads little malware onto your computer as soon as it gets installed. And so that's why, and there's been, I think, multiple examples by now, at least one example where someone spent a considerable amount of time contributing to a high profile open source project that was an npm dependency, and they eventually worked their way into the circle of maintainers of the project. Then the original author of the project wanted to do something else, and they handed over maintainership to that person. And the first thing they did once they had permission to publish new versions of the package is to publish a new version with malware. And I cannot recall which specific dependency this was, but this had already happened. So supply chain attacks like that are very real and dangerous. So I always grab an opportunity to talk and rant about how you should always pin all your dependencies to exactly what you know to be working and safe. And of course, the downside of this is that it gets a little more annoying and tiresome to keep your dependencies up to date when vulnerabilities get discovered in the older versions. But I think personally that it's very, very much worth it, because this gives you control, and this gives you that cozy feeling that the dependencies you have are exactly the ones you wanted. And there's no risk, at least, of this one specific attack happening to you. Okay, let me just stop there and read more questions. Yes, there are ways to sign Docker containers. There's also this new feature in NPM called provenance, which is all about artifacts signing the same way. If you go on the NPM registry, you see some of these packages will have this little badge that says it's cryptographically verified, and that usually means that they've been published with that provenance flag. And then there's this other project, SigStore, which is something that within the Hyperledger Foundation we're actually looking into using. For the same reason, we want to sign our Cacti artifacts. I mean, not just the Cacti, but all Hyperledger Foundation project artifacts. I'm on the technical oversight committee, and this has been one of the task forces that we have open. And Rajiv says locking is also the disadvantage of not letting bug fixes to be not included. Especially tires. Yes. Yes, I agree 100%. I deal with having to bump dependencies manually every day, pretty much every day in Cacti, because we have so many of them, and there's always some new vulnerability being discovered in one of those dependencies that we use. And so instead of just letting it auto upgrade, what I have to do, or we have to do as the maintainers and the contributors, is go in, update the package manually, send the pull request, double check that with the CI that everything still works, and then merge it. And then this has overhead, but it is safer. Obviously, everyone has their own trade-offs. I personally think that the way these attacks are growing in number, specifically supply chain attacks, I think it's worth my time to upgrade it manually, but to each his own. Okay, that was a bit of a detour, but I'm liking the questions. These are very important questions, and I love the fact that I got to talk about these things, even if it was slightly off topic. Very. Oh yes, so I've built the connector image, the connector container image. You can see here how it gets configured. There's log levels, there's the Corda nodes host, local host, and the RPC port, and not so secret credentials, which are fine because these are test credentials. And then you have the ledger container for Besu. You can see that it's a Besu all-in-one image. It's still called Cactus just because we haven't yet had time to rename everything, but in the near future, this will be called Cacti as well, just like the project. And the same goes for Corda. This is a Corda 4.8 all-in-one test ledger that also features the sample application called obligation. So if you go on GitHub, Kotlin, samples, Corda, or samples Kotlin, yeah. And then you go advanced and you go obligation. Then what you see here, this contract is the basis for our all-in-one ledger, meaning that this contract can be deployed to it as well. But that's neither here nor there in the sense that we're going to use the all-in-one Corda ledger now to deploy the R3 Harmonia Lab contracts that have been demoed by Dominic just before I came on the stage. So now that I explained all of the containers in the compose file, we can go to the terminal and start it. Well, actually, it was already running, but I'll just show it running again because I have to delete. Yeah, I have to say down. So I will increase the font size. Yes. So what you see here is Docker compose, and then you tell it to execute this specific file. The command is in the README as well. This is actually a great. This makes it to get a pristine ledger state, because in the previous execution, I was already testing the contract deployment and I was creating assets on the ledger through the REST API. And so it's not a pristine state anymore, but let's say I made a mistake and I just want a clean slate on the ledger and I quickly want to erase it. So then I just do this and then I say up again. And then it boots up. It takes, well, on my machine, it takes a minute or two. But depending on how much RAM and CPU cores your computer has, it could take significantly longer. For example, if if you look here, the memory usage, I'm already up to 22 gigs. And it's growing. So unfortunately, if your machine only has 16, this is not very likely to work at all. So these stack traces, this is the only reason this is happening is because the connector itself is polling the ledger to see when is it finally available. And when it fails, that it just says, oh, I can connect, here's why. But then it retries automatically. So once the ledger says, yes, I'm available, then if I scroll down, it should actually show, yes, that it completed the connector container, completed initialization. And so now I have a REST API running that I can use to talk to the Corda ledger and also the Besu ledger. But right now we'll just focus on the Corda ledger because I'm trying to keep it shorter. Okay, so this is ready, and back to the steps that we had. Right, so then the last step is to build and pull up this little toy front end package that I built specifically for this workshop. It's very, very simple. It's not something that you could use for anything else but this demo, but the important bit here is to demonstrate two things. One is that you can interact with the ledger through HTTP in general. And the second one is that the packages, such as the Cacti Corda API client that we publish, can also be used in the browser in, for example, an Angular application. So if you switch to that directory, and then, well, it's already running for me, but I'll just do it again. So if you switch to that directory and then you say yarn run serve proxy, then it will build the code and it will also set up an HTTP proxy. So now the application itself is running on port 7000, but we also need to be able to hit the endpoints running on port 8080, which is the Corda connector, and on port 4000, which is the Besu connector. And the way we do this on the front end, it will remap the port based on the request of the path of the HTTP request. So all of the plugins that have REST API endpoints in the framework, they all follow this pattern that their endpoints will start with this base path that says /API v1 plugins, and then Hyperledger, and then the package name. So if you search for this expression, you will find a package.json file within the framework source code that has the name that is written here. And this way we can guarantee that there's no collision between REST API endpoints of different plugins. Because, for example, if you have a deploy contract endpoint, that's something that pretty much all of the connector plugins will have. You know, the Corda connector will have that, and the Besu connector will have that. But this way, we don't have to worry about those conflicting. Okay, so now that I explained that as well, we can just navigate to localhost 7000, which is right here for me. And again, this is a very, very simplistic demo, but it shows that what you can do if you step through these buttons. The second one will take a few minutes, just be aware. So if you say list flows to begin with, you get back an HTTP response, and the application is helpfully printing it here. So you see these flows here. These are deployed already because of what I was explaining earlier about the Cacti Corda all-in-one ledger shipping with the obligation example from the Corda samples repository. And now we'll hit deploy contracts, and what will happen then, I will show the terminal here at the same time. So if I hit deploy contracts, then it will take the base64 representation of those jar files that I was showing earlier, the free jar files that contain the Corda contracts, and it sends it to the REST API. That takes it, saves those to a temporary location on the file system, which is of course already not very secure, and that's why the contract deploy endpoint should not be used in production. But barring that, it uploads the files, then SSHs into the Corda ledger, and then it calls the commands that are necessary for it to have the contracts deployed to the Corda nodes, and also B, to create the database schema modifications that are necessary for the contract itself. If you look at the logs carefully, you'll see that the Ledger connector Corda service implementation runs a command that goes roughly like this. It executes the Corda jar file, which has a run migration scripts command. And then what it does there, it locates the manifests or the schema migration XML files, and then it creates the schemas based on that. So then if I scroll down to the bottom, hopefully at this point, it just says that the jar files have been added to the class path. This is also necessary so that when I hit list flows again, now that the deployed jar files are in their place, now if I hit list flows, it will show you the additional flows that these new contracts have. You can see here that we have the EVM interop workflows, Eve to Eve, the swap. This is the same thing that Dominic was demoing earlier. And finally, or almost finally, if you hit issue generic asset, then it will send a request again to the REST API, and it will deploy, or not deploy, sorry, it will create an asset, which is the abstract representation of some asset, for the lack of a better term. And it will return with the transaction hash that has occurred in response to that, and also the flow ID. And the demo application does not have support for this yet, but I have a postman request here, what you can do with this new endpoint called Vault Query, you can send that to the connector, which in turn it then goes back to the Corda ledger and says, all right, give me the state for this specific asset or state table, because under the hood, this is just a database table. And then it returns with the state array or states array. And you can see that the asset name was specified as Cacti Asset 1, which is exactly what the front end code does. I believe it's in API service.ts. Yes. So if you see here, the Corda API client of the Cacti framework has this invoke contract method, and you can pass in a flow invocation definition. You tell it which class the flow belongs to, and then you specify the input parameters for that flow, and the connector will automatically convert this representation into the JVM equivalent objects at runtime. And so what is happening here is that you call the flow called issue generic asset, and you specify that the asset's name should be Cacti Asset 1. And then ultimately this gets persisted into a database table through the inner workings of the Corda ledger. Now, to also showcase how quickly you can develop with this specific example, if you wanted this to be asset 2, then it would get automatically recompiled and this web page would refresh. And if I hit issue generic asset again, it will do it. It will give me back another transaction hash. And if I execute the request to query the vault, now there's Cacti Asset 1, but there should also be Cacti Asset 2. So here you can see end-to-end how from the UI through the backend connector through the Corda ledger, we actually reached the database in the end. And you can see the transaction hashes here as well. Okay. And if you're interested in the exact code that makes all this happen, then you can see here in this API service.ts file, which has a path that I will put on the Zoom chat just to be sure. Yeah, and that might be a good spot for me to stop for a second and look at the chat. Okay, Dominic had to drop. Thanks for joining, Dominic. I know you've left, but maybe you'll see it on recording. Thank you very much for the help. And same for Jim. And no more questions. Okay, I think that covers most of the content that I wanted to show, but let me go back to the README and double check. Yes, so basically that was it. And this doesn't show the entire flow end-to-end that Peter and Dominic were demoing, because that would have taken way longer to explain. But I wanted to instead pick out a small part of it, focus on it, and zoom in to really show you what is the code that needs to be written and how you can make it fairly convenient for yourself to actually develop with it. And so if there are no more questions, then I will just direct your attention to Sean's links once more. And I will also mention one last time the pair programming sessions that we have running every day.
Yep. And if you do have a question for Peter or Marlies, please put it in chat. The links that I just put in chat are going to be in a thank you note to registered folks who registered, but we will also include the links on the wiki page for this workshop, which will have any deck slides or description that you might want to need, or if you want to share it with a colleague, as well as this is being streamed on YouTube. And that video will be on the wiki, as well as the Hyperledger YouTube channel under both Cacti and the workshops playlists. We do have a question from Rajiv. Is there a group email that I can use to send my questions later to the presenters of today? What you could do, Rajiv, is you'll notice under Cacti, there's a Cacti mailing list. I'm going to put it back in chat right now. If you want to send a note to the Cacti mailing list, the Cacti team will definitely see that. You can subscribe to the list there as well. Or you could go on our Discord, and we have the Discord links. Let me repost the Discord links one more time, just so we've got them. But there's the Hyperledger Discord, Harmonia Discord, Cacti Discord, and there's a Discord for Besu as well. And thank you for the question, Rajiv. Cool. Awesome. And there is a Discord channel for Harmonia, Cacti, and Besu, as well as all the other Hyperledger projects, whether graduated, incubating, or the Hyperledger Labs. Any other questions for Peter or Marlies? Going once, going twice. Making sure I'm not muted, but Peter just laughed at me, so I guess I'm not muted. That was good.
We can hear you, yeah.
Listen, everybody, I would like to thank everyone for joining us today, and a special thank you to our presenters, Peter, Dominic, Peter, and Marlies, for putting on such a great workshop. As I mentioned before, we are going to post this to our YouTube. It's going to be in the YouTube channel. It's also going to be on our wiki. The wiki links we just shared. I will put these links as well in the YouTube description in case folks want to catch up and follow along. As Peter mentioned, we have daily pair programming calls for the Cacti team. The Harmonia Lab is active. Definitely check out our Discord. And if you have ideas for other workshops, or you want to see another workshop taking this topic even farther, let us know. Peter, Marlies, any last words for the attendees?
Just thanks for having me, and thanks for staying and listening in. It was great to have you.
Awesome. And thanks again to Peter and Dominic, who had to leave early. We really appreciate their time and all the effort that went into putting together this workshop. And thank you to everyone who attended. We really appreciate you guys being here. We are a community, and we are powered by the folks who attend and participate and contribute and maintain, and we hope you're going to use these projects and get involved. And with that, I'm going to thank everyone and end this workshop. Have a great day, everybody.
Thanks, guys.
Thank you.
Bye.
Bye-bye.
Thanks, y'all.